series of basic chemical process engineering calculation, session 3. So, in continuation to our series, in this session we can check how to calculate the required heat transfer area of the heat exchanger based on the any distillation problem or distillation operation in production plant. In today's case, we have considered the application like distillation of acetic acid, or you can consider it is like solvent recovery. In this solvent recovery session, we are going to recover the solvent as acetic acid, and for that we need to consider one of the particular case, so that we can check the calculation or required heat transfer area, then utility requirement, line size for this particular parameters. So initially we just assume vapor flow rate of acetic acid. We assume here vapor flow rate of acetic acid is approx 450 kg per hour. Okay, we need to consider some basis, so we are going to consider here 450 kg per hour of acetic acid vapors. So we have to calculate the heat exchanger required for the particular application of 450 kg per hour of vapor flow rate. So in production plant or in routine operation, we have to assume or collect some data based on the practical experience, as well as some data we need to collect from the R&D or Google itself. So to calculate the heat transfer area requirement, first we have to check the heat load. So before proceeding to heat load calculation, we know what are the inputs required, what are the input data required to calculate the heat load. To calculate the heat load, we need to understand what is the boiling point of acetic acid. Okay, that means our initial temperature or vapor temperature is equivalent to the boiling point of the acetic acid. So initial temperature of acetic acid vapor. As we know, the boiling point of acetic acid is 117 to 119 degrees Celsius. So we are considering here that. Okay, then we know the equation to calculate heat load. Q is equal to mCp delta T is equal to mCp delta T. So we have first Ti for the vapor, acetic acid vapor, then we know the final temperature of acetic acid. We need to take that acetic acid to the room temperature, or near about 35 degrees Celsius. Okay, then we need to gather the data like specific heat or heat capacity. Specific heat of the acetic acid. Okay, specific heat of the acetic acid, we have to collect that data from the lab or from the Google. So we can put it down kilocalorie per kg of Cp. Okay, then we have to calculate the heat load based on this. So okay, so first we need to calculate the Q total is equal to Q sensible plus Q latent. Okay, because Q sensible is the amount of heat required to increase the temperature from 1 degree Celsius, and latent is the amount of heat required for a phase change. And in this operation we we need both, as sensible heat as well as the latent heat, because it's we are converting from one phase, vapor phase, to the liquid phase. Okay, so to calculate this we require latent heat of acetic acid. Okay, latent heat of acetic acid is 96 96 kilocalorie per kg. Okay, and Cp, we need to correct the unit, kilocalorie per kg Kelvin. Okay, so based on this we calculate total heat load, that is Q. Q is equal to M into Cp into delta T, which is the difference of final minus the initial or boiling point of liquid plus latent heat is like m dot lambda. Okay, okay, we got the kilocalorie heat. Okay, okay, now got the total heat load required to remove. So to remove that much amount of heat load we need to size the heat exchanger. We need to calculate like Q is equal to U into A into LMTD. Okay, log mean temperature. So now to calculate LMTD we have to get the data from the utility as well as from the process. So we consider cooling inlet temperature and cooling outlet temperature. Okay, so cooling inlet temperature is 30 and outlet is 34. You can consider it as 35, 34. If you are using going to use the chilling water, then you have to consider the temperature accordingly, like 10 to 14 degrees Celsius. Okay, so to calculate LMTD we assume that the operation is counter current. Okay, so in counter current we need to calculate delta T1 and delta T2. I'll just go. Delta T1 is that in counter current minus that in minus this is out and this in this out minus utility in. Okay, so in counter current LMTD current is equals to delta T1 minus delta T2 divided by ln of delta T1 by delta T2. Okay, so that is the log mean temperature difference. Okay, we got LMTD. Now we have Q, we have U. That means we have couple of parameters like the heat transfer area and the U, which is overall heat transfer coefficient, both the unknown entities. So to calculate the area we have to check the overall heat transfer coefficient, and that can be overall heat transfer coefficient. Okay, overall heat transfer coefficient U will get, you can consider that the U based on the graph which is provided in Paris handbook. So for the water versus the organic solvents. Okay, here you can consider that between for shell and tube heat exchangers 150 to 200 uh, kilocalorie kilocalorie per hour kilocalorie per hour per meter square Kelvin. Okay, so we are considering here 150 on safer side, because if we assume that for the initially we'll get up to 200 kilocalorie per hour meter square Kelvin also, but after certain time there is scale formation and all these things for shell and tube. We can mention here for shell and tube type. Okay, so now we have overall heat transfer coefficient, then LMTD and Q. So we can calculate simply area required dividing the total heat load into LMTD and the overall heat transfer coefficient. So we'll get the required heat transfer area, which is approx the 15 meter square. So in this way you can calculate for the any of the distillation operation. You can just change the parameter, whichever. For here we have considered acetic acid. You can check that calculation with different solvents like xylene, toluene, or whatever solvent recovery setup you have. I hope you have got the idea about how to calculate the heat transfer area requirement based on the vapor flow rate and all these things. Okay, so in next session we can cover the utility sizing for based on this calculation as well. If you have any questions in this, you can drop me in comment section as well, or you have any suggestions or any specific calculation requirement or any concept on which you expect to I have to prepare or present a video session or lecture, you can drop me in comment section also. Okay, so we just CP, then Q total, then latent heat lambda likewise. Okay, thank you. That's it for now. We'll meet in another calculation series in next video. Thank you for now. Bye bye.